Hi, let's dive into lesson 5 handout where we go over heuristics. The first problem is a review. We're organizing the 5 search strategies we learned into whether they use the forward cost, H, backwards cost, G, both or none. Uniform cost search uses only the computed backwards cost by definition. Greedy uses only the estimated forward cost, H, by definition. A star uses this equation right here to calculate F, total cost. So it uses G and H, both by definition. Meanwhile, we have depth first search and breadth first search, which don't care about G or H at all. They only care about the order that nodes are inserted in, and then whether they use a stack or queue to pop them off. Neither of the costs are considered. Number 2, A star breaks in this graph. Why? I circled it right here. The heuristic of A is 6, which is greater than the true cost of A to G, which is 3. This violates the rule of admissibility, which states that the heuristic must be greater than or equal to 0, and less than or equal to the true cost. And actually, we have a second violation right here, where the heuristic of S is greater than, scratch that. Give the definitions of admissibility. We just talked about how the heuristic must be between these two things. Consistency is a little bit less intuitive. The equation is a little more complicated, but basically it's saying that the heuristic of A minus the heuristic of B must be less or equal to the cost of A to B. And we'll talk a little about that more in the next problem. So number 4, it's asking us to detect violations in admissibility or consistency in these two graphs. And the first one, admissibility is violated because we have a heuristic of A is 15, which is greater than the true cost of A to G, which is just 5, as shown by this one edge right here. In the next graph, we have consistency. Where we have an instance that the consistency rule is actually violated because HA 30 minus HB 5, so 25, is greater than the cost of A to B, which is 10. So 25 is greater than 10. And if we remember the rule right here, let's actually look at what this rule is saying. So this is the rule. It's saying that if our cost from A to B is a certain value, so 10, then we can't travel closer to the goal than 10 and if we can't travel closer than the cost to the from A to B to the goal, then how could our heuristics change by more than that? If it takes 10 steps to go from A to B, then why do we think that we got 25 steps closer to the goal? In other words, our heuristic is inconsistent, and it could lead to some traps when we navigate our algorithm, execute our algorithm. We'll run into some inefficiencies. What does it mean for heuristic A to dominate heuristic B? That just means that at all points, at all nodes n, heuristic A is greater than heuristic B. Why? Because we will often combine two heuristics, A and B, with a max. And I believe this is actually more than or equal to. And if heuristic A is always more than or equal to heuristic B, then heuristic B doesn't even need to exist. It's just irrelevant. And you might as well just do H equals to heuristic A and not consider heuristic B. Finally, we have a bunch of statements, and we're trying to see if they're admissible heuristics. So the first one is inadmissible. Why is it inadmissible? Because you can think of an example where, let's say, our true cost from A to B is 3, and our goal is to get from A to B. So our true cost is 3. And then we have a heuristic, one heuristic that's, we have one heuristic. Let's actually write the letters in. H sub A is 2. This is admissible. The H sub A heuristic is less than the true cost from A to B. And let's do another one. H sub B of A equals to 2. This is also admissible for the same reason. And then we'll have one more just for kicks. H sub C of A is 2.5. So heuristic A, heuristic B plus heuristic C, if you add them all together, it becomes 2.5, so 6.5. And 6.5 is greater than H star in this case, which is 3. So that's an example of why A is inadmissible. For B, this is admissible. Why? Because if all 3 heuristics, heuristic A, heuristic B, and heuristic C, are all admissible, then taking the lowest one can't possibly increase that over the limit. So, admissible. Maybe one day I'll learn how to spell that. For the same reason, if these 3 heuristics are all admissible, then taking the largest one is still going to be admissible. And right here, we're essentially taking an average of all 3 heuristics. And that is also going to be admissible because you can't you can't have a number that's greater than the largest one or less than the lowest one from taking an average. And finally, 0 is admissible because it can never violate this rule. It's always going to be, it's just 0. It's no heuristic. All right, thanks for watching. Good luck with class.